All right, this is homework number 6. The first part of the problem says, explain why the evaluation of the integral is incorrect. Use the integration capabilities of a graphing utility to attempt to evaluate the integral. Now, my screenshot has the graphing calculator. The issue here is that there is a discontinuity at 0. So 1 over x squared is undefined at x equals 0. So you would have to split this into two integrals and use limit notation. Let's see what happens in Desmos. You're finding out with me in real time. Integral from -1 to 1 of 1 over x squared dx. Okay, so yeah, similar. It doesn't explain why. The graphing calculator at least said divide by 0. But yeah, we get an error here, or it says it's undefined. The question is it actually undefined, or could we get an answer out of this if we use limits? So they're not actually asking us to go through and evaluate, but just because it says undefined doesn't mean the answer is no solution. All right, let's take a look at, let's see. Oh, do I need to determine? Let's see. Yeah, I'm just going to, I'm not going to evaluate this one. Okay, so then 17. The integral from 0 to infinity of e to the negative x dx. So let's see. The graphing calculator, you can see I put in 1e99, told me that this answer is 0. So let's see. Could that be right? So this would be, let's think about this graph. E to the negative x. It's a graph that goes through 0, 1, but it's been reflected around the y-axis. Looks like this. And if we're going from 0 to infinity, there's no way that the area under this curve could be 0. It does approach 0, but there's definitely positive area under here. So there's no way this could be right. Let me see what this looks like again in Desmos. I'm not sure if I can type in infinity here. Infinity. Ooh, let's see what happens. Oh, now see, this tells me 1. My graphing calculator, I couldn't type in infinity. I could only type in 1. What was I doing? I was doing 1 times 10 to the 99th, I think is what I was doing. Okay, now that says 0. That's kind of interesting. But here, if I say infinity, I think maybe this is the right answer. Again, I'm going to, in interest of time, I'm not going to actually calculate through, but that's interesting. Let me screenshot that. Let's pull this and just make a note that, actually, I need to do it in a better spot. Sorry. Let's go ahead and just make a note that this actually gave me a different answer, possibly the right answer. 1 seems reasonable to me because you have a height of 0, 1, and then yeah, I don't know. I think that might actually be possible. Okay, let's take a look at number 19. So determine whether the improper integral diverges or converges. Evaluate the integral if it converges. So remember, we know about p integrals. P integrals are in the form, the integral from any constant. Well, I guess actually, if we're going to find the actual answer, it goes from 1 to infinity of 1 over x to the p dx. This would be a p integral, and it converges as long as p is greater than 1. So that's our rule here. Diverges if p is less than or equal to 1. So this is a p integral. P equals 3, which is greater than 1. So that means that this converges. I'm going to call it a convergent p integral. And what does it converge to? It converges to 1 over p minus 1 in general. So this is going to converge to 1 over 3 minus 1. So this converges to 1/2. For the next one, this is not a p integral. This is a product of two functions, and it looks like it's integration by parts. I'm going to use the tabular method. Remember, we use Lyautey to pick what u is going to equal. And make sure in your table that you label these two things. U needs to be the algebraic part. Exponential would be my last choice for you. So u is x squared. dv is e to the negative x dx. So remember, the way that this scenario works, we take derivatives of u until we get to 0. We integrate e to the negative x dx. Now remember, there would be some u sub happening. So the integral of e to the u is e to the u. Du would have been equal to negative dx. So there's going to be a negative. Let me get the u out of there. Sorry. Negative e to the negative x. And then integrate that. And again, you're going to get another negative. So you're back to e to the negative x. And wait, do I need to do? Yeah, I need to do one more. Sorry. So then integrate that, and you're back to e to the negative x. These signs are plus, minus, connect diagonals, and swoop around the bottom. And we shouldn't have any integral left after this. This is going to be, we're going to use limit notation here. The limit as b approaches infinity of, so we have, let's see, because that's b. We have negative x squared. Instead of writing e to the negative x, I want to write negative x squared. I want to write over e to the x, because anytime you're evaluating plugging something into a negative exponent, you want to make sure you know whether that thing is really in the denominator or not. Okay, so that's that. And then minus 2x times e to the negative x, so minus 2x over e to the x, plus 2 times negative, so minus again, 2 over e to the x. Technically, this is like plus the integral of 0 times e to the negative x, but that's just 0, so we don't need to worry about that. We're evaluating from 0 to b. Again, remember your limit notation. So now this is the limit as b approaches infinity of negative b squared over e to the b minus 2b over e to the b minus 2 over e to the b minus 0 minus 0. This last term is not 0. It's minus 2 over e to the 0. Now, you don't have to do L'Hopital's rule here, but if you were being very extremely thorough, technically that's what's happening. But informally, I can think of function races. I also don't think you have to show L'Hopital's method on a free response like this. We can very easily say a quadratic does not outrun an exponential, or linear doesn't outrun an exponential, and neither does constant. So these are all going to 0 here. And then this is positive 2. So I should get 2. Now, the fact that I got an answer means that this integral converges, and that's what it converges to. So 0 to infinity, that integral of x squared e to the negative x dx equals 2. In other words, the integral converges to 2. All right, for number 30, now we have the integral from 1 to infinity. Let me set up my limit notation so I don't forget about it. I should have done this on the last one. Not that I forgot, but still. All right, this should look kind of familiar. It's not integration by parts because u sub should work here. If we let u equal natural log x, then du dx is equal to 1 over x. And so that's going to cancel out here, right? X times du is equal to dx. So those x's cancel, so you get u is the natural log of x times du. All right, so keep your limit notation. The limit as b approaches infinity of, this becomes u squared over 2, but let's go back to ln x squared over 2, evaluated from 1 to b. And then you can't just get right down to the answer. You should show that you're plugging in b before you take the limit. Ln of b squared over 2 minus ln of 1 squared over 2. What is the natural log of infinity? Remember, the natural log graph looks like this. So as x approaches infinity, natural log of x approaches infinity. So this is infinity minus ln 1 is 0. So that's infinity. So the integral from 1 to infinity of ln x over x dx equals infinity. Therefore, the integral diverges. Sorry, I'm a little congested here, so if I sound weird or if I have to take some pauses, that's what's happening. Okay. Number 34. We have e to the x over 1 plus e to the x. Remember, you are not allowed to do this and start breaking things up. That's illegal math. I have a little note here. The limit as x approaches infinity of e to the x over 1 plus e to the x equals 1. So the reason I'm pointing that out is because the graph is not even approaching 0. So far, this graph is, let's see, is this graph approaching 0? Yeah. This graph is approaching 0 because x will grow faster than ln x. So it had potential to, this had the potential to converge. X squared over e to the x is approaching 0. Those terms are approaching 0. 1 over x cubed is approaching 0. So all of those had potential to converge. The question is, are they decreasing fast enough? So these terms are approaching 1 and they're going to level out. They're never going to get lower than 1. So that means that there's no way this could, there's no way that this function decreases fast enough for it to converge. So I know that this diverges right now. But if I'm given a free response question, I'm not sure if I would risk explaining that or not. And this will make more sense when we get to chapter 9. We'll talk about this idea a bit more. But just so you know, you can kind of think about, are these terms even approaching 0, so that I can figure out if I even should have an answer or not. Okay. Sorry, one more thing about that. That only applies to, that rule only applies to integrals where we're looking from a constant to infinity, like we're going on forever. It wouldn't be if there were just a discontinuity and I were going from 0 to 1 or something like that. Okay, anyway, this is u sub. U can equal the denominator, 1 plus e to the x, because du dx will be e to the x. So that's going to cancel this out, right? Du divided by e to the x will equal dx. So now it's the limit as b approaches infinity, the integral from 0 to b, of 1 over u du. And that's equal to the limit as b approaches infinity of natural log of the absolute value of 1 plus e to the x. The absolute value is not necessary. This is positive, but you can leave it in there. Show your substitution before you take the limit. So this would be the natural log of 1 plus e to the b minus the natural log of 1 plus e to the 0. The natural log of 1 plus infinity, the natural log of infinity, we talked about that before. The natural log of infinity is just going to keep growing. So it equals infinity. This is the natural log of 2, but infinity minus a constant is still just infinity. So, like I said, it should diverge, and we just proved that it does. Okay, number 35. Same idea here. This is a cosine graph. It does have a change in the period, but it's still, as we approach infinity, remember the cosine graph is just going to like keep cycling in and out like this. So I'm never going to get to a finite answer, even though it is symmetric areas. Like you might say, well, oh, okay, well, it's going to be 0. Well, no, because you keep adding an extra area or subtracting one or adding or subtracting. Like it's not, you're going to keep bouncing back and forth between positives and negatives. You'll get like a range of areas, I guess. So this should also be diverge, but let's go through and show why that would have to be true. All right, we're going to need some u sub here. U is pi x. Du dx is pi. Du divided by pi is dx. This is now u. So the limit as b approaches infinity of the integral from 0 to b of the cosine of u du. Oops, I forgot my constant. I need to slip in a little 1 over pi because it was du over pi. That equals the limit as b approaches infinity of 1 over pi of what? The integral of cosine is sine. Instead of u, I'm going to put my pi x back in there, and I'm going from 0 to b. The limit as b approaches infinity of 1 over pi. The 1 over pi can be brought out in front of the limit as well. I don't think that matters. This is the sine of bx. Oops, sorry. Sine of b pi or pi b, whatever, minus the sine of 0. The sine of infinity, again, will keep cycling through between values, right? It's going to stay stuck between positive 1 and negative 1. So we're getting this value that's like 1 over pi. So this is always 0, but it'll basically be like some value between, this will be some value between, let me put infinity in here actually, between negative 1 and 1. And so I'm not getting down to a finite answer. The area will keep going back and forth between negative 1 over pi to positive 1 over pi. So that means that this integral diverges because it's not converging to a single numerical answer. I can tell you what the area will be between, but I can't say that it converges to one single number. Okay, for the next section, it says, find the area of the unbounded shaded region. It's a bit hard to see the shading here, but it looks like, oh, I guess they have it defined there. Never mind. So we're just supposed to set up this integral here. Oh, why do I have, oh, never mind, sorry. Okay, so this is the integral from negative infinity to 1 of e to the x dx. Excuse me. So this time my limit notation should say the limit as a approaches negative infinity, and now it's the integral from a to 1. And that equals the limit as a approaches negative infinity of integrating e to the x is just, oh, it says e to the, no, yeah, e to the x. Sorry. I keep switching, my eyes keep switching down to the next problem. Sorry. Okay, so the integral of e to the x is e to the x from a to 1. This becomes limit as a approaches negative infinity of e to the first minus e to the a. And that becomes e minus e to the negative infinity, e minus 1 over e to the infinity. That's 0. So this is e. So this integral, this area, is equal to e. Okay, the next one Consider the region satisfying the inequalities. Find the area for part A. Part B, find the volume of the solid generated by revolving about the x-axis. And I don't quite know why, but I'll go with it. I did not do assign the y-axis revolutions. You can do that one for fun, and then check it in Desmos if you want. Okay, so for this one, and this is our last problem here. So I want to sketch the graph. I always like to sketch the graph first. We're looking at e to the negative x. So remember, exponentials, you put in 0 and you get 1. E to the negative x is decreasing as we go on. And we're only looking for y greater than 0 and x greater than 0. So that's why I didn't extend it on up here. All right, so first I want the area. So the area should be the integral from 0 to infinity of e to the negative x dx. And did we already do this somewhere? Did we? No. Okay, fine. So du dx would be negative 1. Negative du is equal to dx. So this is the limit as b approaches infinity of the integral from 0 to b of e to the u du. And that's the limit as b approaches infinity of e to the u. Oh, wait. Negative. Sheesh. Okay. Sorry. I keep doing the u sub and then not actually putting it in. So I'm going to keep my negative out here. Negative e to the negative x from 0 to b. When I actually plug in b, I'm going to rewrite this as 1 over e to the x. So 1 over e to the b minus 1 over e to the 0. Now take that limit. 1 over e to the infinity is 0 minus 1 over 1. Negative 1 is positive 1. So the area under that curve is equal to 1. For part B, we are revolving the region about the x-axis. I still like to have a sketch. So here's my little representative rectangle. It's got R. And if we rotate this around the x-axis, we get some sort of like funnel-looking type shape. So the radius of revolution is top minus bottom. Top is e to the negative x minus the axis of revolution, which is just 0. And remember, volume is pi integral from a to b of r squared dx if we're just using disk method. There's no washer here. Okay, so this would be pi times the integral from 0 to infinity of e to the negative x squared dx. Let's clean this up before we get into u sub and stuff. So actually, I'll do it down here. The limit as b approaches infinity of pi times the integral from 0 to b of e to the, when you raise an exponent to an exponent, you multiply your exponents, so it's e to the negative 2x dx. U sub off to the side, u is negative 2x, du dx is negative 2, du divided by negative 2 is dx. So now it's the limit as b approaches infinity of negative pi over 2 times the integral from 0 to b of e to the u du. The integral of e to the u is e to the u, so e to the negative 2x from 0 to b. Okay, and now, again, negative exponent, so I'm going to write it as 1 over e to the 2b minus 1 over e to the 0. That's negative pi over 2 times 1 over e to the infinity is 0 minus 1 over 1. Negative pi over 2 times negative 1 is pi over 2. So the volume is pi over 2. And yeah, if you were going around the y-axis, I would guess we would be going from 0 to infinity or 0 to 1, but 0 is not attainable. So maybe that's where the. Oh, yeah, because your function would be, if you are going to do part C, you need to change this to like, let's see, ln y equals negative x. And so negative ln y equals x. And then you'd be like trying to integrate that. So interesting. All right, I'm not doing that though for the length of this video. So if you try part C, go for it and then see what Desmos tells you. I'm actually curious because I know my graphing calculator doesn't normally do this. So sorry, I do want to see what it says about this. So, oh, see, we did do this somewhere. Okay. What did I have? Now I had 2x and I had pi, and that sure looks like pi over 2 to me. Yeah, cool. Okay, Desmos can do it. That's really nice, but know that these definitely could be non-calculator problems.